Assalamualaikum and good afternoon, guys. Can you hear me? Can you hear me?
Yes, brother, can hear you.
Okay. So without any further ado, we continue our revisions for preparation for tonight. Test 1, 2016 and 17. This question already read by our brother Mukri. So you are given this figure Q1 block diagram. This one is a P controller. This one is the plant model. Okay. And this one is the actuator. Okay. Right. So to construct the rule locus for the system, minimum conditions, some rules can be defined without inspection. Okay. Choose applicable. All right. So shall we plot it? Okay, based on the given transfer functions. So we have open loop zeros at -9. Open loop poles at 3 point, -1, -2, -7. Okay. So we start from the origin. Rule locus start from the poles ended at zeros. So this one. Okay. And then we will go something like that. Okay. Ended at infinity. Then this one is start from poles and ended at zeros. Okay. So question is breakaway point. Is there any breakaway point in this plot? Yes, we have here. Okay, is a breakaway point. So it's available. Okay. And the real exists. Okay. Maximum gain. Okay. Break in. So break in usually happen between two zeros. So there is no two zeros, only single zeros. So not available. Okay, not available. So this one is more minimum gain, not available. Angle of departure also not available. Angle of arrival also not available. Okay, this one angle of departure usually reason no complex conjugate poles. Angle of arrival not available due to no complex conjugate zeros. Asymptotes, is it available? Yes, it's available. Okay, because number of poles is greater than number of zeros. Okay, so sketch the rule locus. We already sketched just now. So we have to check whether this point is it on the rule locus. Okay, part C. -1 plus J1. So check. Okay. So we have to use the angle criteria. Okay, minus angle of poles equal to 180 degrees. Okay. So for that purpose, we have to do some drawings. Okay. then this is the point. Okay. And we have to measure the angle. Okay, angle for this. Okay, measure the angles. So I measure the angles theta 1, theta 2. Okay. So theta 1 is over here, which is theta 1, theta 2, theta 4. So theta 1 is 90 degrees because it's aligned with the poles and test point. Theta 2 is 1/1, which is 45 degrees. Theta 3 is tangent 1/6. And then theta 4 is 1/8. Okay. So when we applied the calculations, okay, according to this formula, okay, so the total is 77.125, 9.46 degrees. So it is 137, which is not equal, minus 180 degrees. So therefore, is not a point on Locus. Okay, because fail to fulfill angle criteria. Okay, so that is C. How about D? Point on the locus that give a dominant close to pole zeta 0.7071 is -4 plus J11. Determine the required setting for the P controller. So calculate the gain value. Okay. 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 So this is the dominant pole given in question. Okay. So okay, given minus 1.4 plus J 1.4. So the gain value at for the P controller, okay, we just take the equation just now, which is S plus 1, S plus 2, S plus 7, S plus 9, okay. Which is from the transfer functions here, okay. And insert the value here inside, okay. So you will get 1.656, okay. Then you just straight away calculate for the TS and TP. Take the real part, 1.4 take the imaginary part. Okay. And then since zeta is given, so for overshoots, okay, for the overshoots, straight away you use the formula which is given as, sorry, (4.32). If you can't remember the formula, okay, just straight away go to the attachment, and then you will see this formula. Okay, you don't have to memorize now, eh? It's already there. Okay, and then finally the last part, which is F. Comment on the validity of the second order approximations on the third pole locations. Valid or not valid? So just find the characteristic equation for the validity of second order approximation. The gain K should be increased so that the ratio for the third pole determined is greater than 5. So you just calculate the characteristic equations, okay, which is S plus 1, S plus 2, S plus 7, S plus 9 equal to 0. Okay, so K is equal to 1.656. Okay, so you insert inside, okay, then you will find the S cubic plus S square plus S plus the K value, okay, equal to 0, right? And then you find the roots and check the third pole. Check the third pole value and then find the ratio. So the ratio is the third pole value divided by 1.4. 1.4 is the real part of the dominant pole, okay, and it is mass greater than 5, so that we can apply second order approximations. Okay, understand?
Excuse me, doctor.
Yep.
When we check for the ratio, could we have also checked it with the with one of the other two poles?
One of the other two poles.
Meaning since it's
okay.
S cubic, we will get 3 roots, right? So can we check it with the one of the other two roots that's gonna come?
When you find the roots, so you will have a third pole and minus 1.4 plus minus J 1.4. So you already have this one, which is the same as the previous slide. Yeah. So you find this one.
Yes.
Okay. Okay.
Sorry, doctor.
Yeah.
But in the question, the hints given that we are not necessary to calculate the poles. So got other way to solve this question?
Okay, so you can just write for the validity of second order approximations. Okay, the gain K should be increased. Okay, so that the ratio for the third pole and dominant pole, okay, real part is greater than 5. Or you can write like this also can. Okay, so if you cannot write like this, deep understanding on the K variant, so you can choose this one. Okay, no problem. Hint is just a hint. You can follow or you don't have to follow. Okay.
Okay, thank you, Doctor.
Okay, share. Right. So we go to the next question, which is question number 2. So PI and VI are used to improve the performance. Then give the general function of each controller and state performance that can improve by those controllers. So this one is from the book, from the notes, from the slides. So PI is for the PI improve steady state error. Okay. ESS equal to 0. PPI. So we have a gain K. Okay, S plus 0.1 divided by S. Okay, so you just follow me lah. You choose this one, S plus 0.1 over S. Okay, so it's very near together. Can cancel out, but at the same time, it increase the system type. Okay. PD is for the improved transient. Okay. FK over there. Right. The next question is, that is a theory. Okay, so you are given the zeta. Determine the open loop transfer function of the system. Oh, okay. So you are given a plot here. So identify the open loop poles. Safwana, what is the value of open loop poles? Nur Safwana. Open loop poles from the figure here.
For the 0, S plus 3. S plus 8.
S plus 8. Open loop zeros. Open loop
minus
zeros.
8. Minus 8.
Open loop poles.
Minus 6. And then negative 1. Ni berapa ni?
Tu dah tulis?
Okay. Negative 1 plus minus J1.
Tak fokus. Exam ni tak fokus.
Saya tengok kertas. Sebab saya print out.
Okay. So, and then you will get the S open loop. S what? Nick. Oh, Nick Muhammad.
Yeah, Prof.
Apa dia GS?
Yes. S plus 8 over S plus 6. Ya, yang ni S squared plus 2S plus 1 plus 2 lah.
Demo tak hebat lagi lah, Matt. Kena train lagi ya. Right, so you have to read. Okay, so be careful. GS is not given. So GS information is inside the plot. So I hope everyone in my class can produce such thing from read from the graph given, identify the open loop poles, identify the open loop zeros, and construct the open loop transfer function. Okay, Nick, boleh?
Okay, Prof. Boleh.
InsyaAllah. InsyaAllah malam ni. So estimate the controller gain K, the settling time, the peak time, and the steady state error. Okay. So we have to find the dominant pole first lah, isn't it? You gonna cari what is the dominant pole. So how to find the dominant poles? Farhan. How to find the dominant pole? Tak datang. Yuki Wong?
Yes, doctor.
How to find the dominant pole?
By plotting the zeta line on the graph.
All right. By plotting the zeta line, zeta line 0.5. So theta is equal to 60 degrees. Okay. So you have to print this one lah. Have to print this one. Otherwise, difficult for us. Okay, to get the values. Printer ready, Yuki Wang, you have printer?
Yes, doctor.
So 60 degrees, something like that, Okay. Sini mah. Safwana, since you already print out and draw the zeta line 60 degrees, can you give me your dominant pole, please?
Itu baru nak draw.
Malas-malas tak buat
Malas-malas tadi.
Bagus.
-1 plus 2J, plus J2.
J2, Anybody? Jason Lau, have you got the dominant pole? Jason Lau absent. Simi Chin?
Doctor, I haven't print out.
Okay, good. 1.6. The answer schema is 1.6. So, Wana, if you get J 2.0, okay, ma. No problem. Okay. Dominant pole, right? Then this is the real part. Real. And this one is the imaginary. Okay. Then easy, ma. So you can calculate everything inside here. Okay. K, TS, TP, and steady state error. Easy. So TS, TP, 4 divided by 1, 4 seconds. 4 pi divided by 1.6. Okay. 1.96 seconds. Okay. K. Ismail, how you calculate K? Okay.
Yes, doctor.
K.
Magnitude criteria.
Yeah. Can you
Yes.
can you read for me? K I think is S plus 6, correct? S squared plus 2S plus 2, correct? Now S plus 8, okay. Then the dominant pole is S is equal to -1 plus J 1.6. You enter inside. Okay. Become Haza, it's fine.
Just a few seconds, sir.
Uh, One point 1.14. Okay. Ifzul. Ifzul. Datang. Astaghfirullah.
Ya saya doktor.
Ifzul. System type apa? What is the system type of the GS?
System type 0.
Type 0 eh? So you use KP kan? So what is KP? Sekali lagi limit S to 0. Okay. KDS. Okay. So ada dekat formula tu kan? Ya. Ada tak? Ni. KP, KV, KA. This is type 0, type 1, type 2. Okay. So the KP is 1.14. Okay. S plus 6. Okay. So KP is 0.76. Okay. So Wahidah, not Aina Wahidah. So what is the value of the steady state error?
0.
0. Kejut. Kejut aku.
1 over 1 plus KP.
7, 6. 5, 6, okay. Okay. Alas. Okay. It is important to have a 0 steady state error while keeping the system operate. Is it possible to design a controller to replace computational gain so that we can get ESS 0? Wahida, is it possible?
Yes, sir.
Okay. Is it possible to replace P controller with something that give steady state error 0?
Possible.
Possible. Yes, it is possible. Using Wahida, using
Using VI controller.
betul. Okay. Boleh lah, pass. Tu naik pass lah. So, what value you want to use? You follow your lecturer lah. 0.1 over S. Okay. And then you combine with the open loop. Okay. Then find the K. Okay. Find the K value. Find the P value, which is S plus 6. Okay. So replace with the -1 plus J 1.6. Okay. Put it aside. Then you will get same key. Okay, but the KP is different. So KP now is different because we have a new one, which is 1.4, 1.14. Okay, so KP is infinity. So that's why 1 over infinity 0. Okay. Draw the complete controller diagram, including the controller with the value of gain KP. Okay. You have to draw. So we draw. Okay. GPI. Okay. Then draw the block diagram.
Excuse me, doctor. Could you go back a
Okay.
second?
Yeah.
Doctor, I'm confused about this part, like whenever we have to get the KP and KI. Right now, you use the value of KP as 1.14, right?
Yep. Yep. 1.14. This one, KP, I use 1.14.
So it's the same as K.
Yeah, it's the same as K. It's a proportional. It's a proportional. It's like a potentiometer in reality. Okay. So you vary this one. So you actually in the system is have the device have three legs. Okay. So you tune here. You tune the value of the KP using a screwdriver over here, or using a knob. Okay. So I think it's high time for all of you to enter to the laboratory lah, right? Because you can see and feel what is the device, the hardware that used. Okay. Right. So okay. So this is the input R. Okay. This is the KP and KI, which is goes here. So this one is the PI, the I part, which is 0.114 over S. Okay, and this is the open loop pulse, and then it will be negative feedback. Okay, خلاص. Okay, خلاص. So we go to the 2017. Okay. I invite Con Yawen. Miss Con?
Yes, doctor.
Yeah. Can you read?
The plant is controlled by a proportional controller K as shown in figure Q1.1. The root locus is shown figure Q1.2.
Okay.
A controller is needed to maintain the system at settling time TS of 2.6 seconds with no steady state error. A. From the root locus, find the range of K such that the system is in underdamped condition. B. What happened to the system if K in part A is increased to the maximum value to reduce the steady state error? Sketch the output response of the system in this case. C. Determine the dominant closed loops for the settling time above. Hence, find the corresponding damping ratio, zeta. D. Calculate the value of the proportional controller K and steady state error ESS at the dominant poles in part B. E. Design a PI controller so that the steady state error ESS is equal to 0.
Thank you. All right, so plot is given. Off your microphone, please. Okay. Plot is given. Okay. So third order. Type 0. Okay. The controller is needed to maintain the system at settling time 2.6 seconds with no steady state error. Okay. So how to do? From the locus, find the range of K such that the system is in underdamped conditions. Okay, underdamped. So what is the underdamped? Underdamped is this region. Okay. This is underdamped region. Okay. Right. Okay. So we have to find the over here. Okay. This is where K critical and zeta equal to 0. Okay. And this one is the breakaway point where K that will give you zeta equal to 1. Okay. Critical damping, not critical gain. So the question asked, okay, understood. So you have to calculate identify what is the 2 points. Identify 2 points, i.e. breakaway point, yeah, and intersection RL and J omega exists. Okay, so from the graph. See Michin, can you give me this point? What is this point? And this point?
I think it's 0 plus 6.5 J.
0 plus
6.5 J.
6.5 J. Not like that. You just said J 6.5. No need to mention 0.
Okay. Another one is negative 2.
Negative 2.
Yeah.
Okay. The answer script, the answer schema negative 1.95. Okay,
Okay.
Sesuai lah. Okay, lebih kurang lah. So BAP negative 1.95. Then RL intersection with the J omega is J 6.5. So we calculate the gain. What is the gain value for this 2 points, so that we can see the the under dam range gain K. Okay, so straight away, okay, use the S plus 1, S plus 3, and S plus 10, no zeros. Okay, so divide by 1, okay. So insert S equal to negative 1.95. So K is equal to 8.0. Okay. Then for the other one, K is equal to S plus 1, S plus 3. So replace with minus, positive J 6.5. So you get K critical, which is equal to K critical at RL intersection with J omega. Okay, guys. Okay. Therefore, the range of under dam, the range of under dam for gain is 8 multiplied by K multiplied by 56560.3. Okay, understand? Okay, Asif, paham?
InsyaAllah ada.
Alhamdulillah. What happened to the system in K, in part A, is increased to the maximum value to reduce the steady state error. Sketch the response. Maksud dia. Maksud dia. What happened to the system if K in part A is increased to the maximum value? So the maximum value is maximum value of K is K max ni 560.3 lah. So USS equal to 0. Okay. So is it what happened? Patrick, what happened? This one is an open-ended question. It's not easy, you know. So maximum, Patrick.
Yeah.
So maximum is 560, which is equal to K critical. Okay, very critical. Which is zeta equal to 0. Okay, so therefore the response will oscillate when time towards infinity. Okay, so it's like this. Goes up. Okay, it's oscillate. It's critical. Okay, so because it's very near to the border. Okay, if you look here, Okay. So this is the critical gain. So this part is the right-hand side is the unstable zone. So this J omega is where the critical gain happen, and the response will be oscillate. Once it goes to the right half plane, so the response will be oscillate, but will become bigger and bigger, unstable. Okay, that is the answer for the question part B. Okay, determine the dominant closed loops for the settling time above. Hence, find the corresponding damping ratio zeta. How to do it? So given in question that settling time is equal to 2.6 seconds. Okay. So TS is equal to 4 divided by real, which is equal to 2.6. That's why the real part, which is theta omega n, is equal to 4 divided by 2.6, which is 1.54. Okay. So we want to find the value of zeta. So how to do it? Chong Juan, any idea?
No.
No idea, Chong. Ayo, this one, Chong Hui Ki. Yeah, man. Come on, man. Tahu, Chong Hui Ki. Okay lah, si Michin.
Draw a line. Draw a line for 1.54 and see what is the value for the imaginary. I think like that. I also don't know.
You also don't know.
I think it's just
Okay.
draw a line for one.
Wait. This is real part kan? Negative is a negative kan? Negative zeta omega n and negative 1.54 because it's on the right half plane. So yeah, I think it's any. Minus 1.54 is somewhere here. Let's see this one. Can you see what I draw? Guys?
Yeah, can.
This one negative 1.54 and the new real from these calculations because we are given this one. Okay, so this is the new real, not the previous one. The previous one is the old one. Okay, the new one. Okay, so minus 1.54. Then you go up, you go up, then they touch the root locus, they touch the root locus. Berapa? Si Michin? Berapa?
2.2 J. Yeah.
2.2. Kira balik macam jauh sangat. Safwana?
Leave that there.
You draw straight line. Negative 1.54 straight line. Berapa? Straight line. Daripada minus 1.54, straight line intersect with the root locus.
2.55, Doctor.
2.55. Okay, something like that, eh? So
2.65.
2.65, okay. J, the answer is 2.8. 2.65, okay. Si Michin, 2.4, eh? Dia punya,
I haven't print out, so don't know the exact one.
So 2.8, okay? 2.8, okay? So a draw IG straight line at minus 1.5 up to cross the RL. So then draw, then the apa mau cakap macam mana? Then the intersection of straight line with RL, okay? Draw a straight line again to the right, okay? To the right, IE plus J 2.8, okay? Plus J 2.8. That's why dominant pole is equal to minus 1.54 plus J 2.8. Natra, faham tak?
Faham Doktor?
Faham? Faham? Natra, faham tak?
Faham Doktor?
Natra, faham tak?
Belum?
How you get 2.8?
2.8 draw from the real axis to the root locus.
Okay. Then
And then find the value.
turn right.
Turn.
Right
at the imaginary axis.
Okay.
The intersect.
Okay. So, Atika? Nur Atika?
Yes, bro.
So how you find the zeta? So you have this line, Tika? Oh, Tika?
Yeah.
Silap. Yeah, this line. And this one is 1.54. This one is 2.8. So theta dia.
English tangent 2.8 over 1.54.
This
is the fuck off.
61.19.
Okay. So zeta is Tika?
0.482.
Okay. Chong Hui Ki, now you understand?
Understand.
Calculate the value of proportional controller K and steady state error at the dominant poles. Easy lah. Easy. So K is equal to So K is equal to K. And then the steady state error. .67. Then the steady state error will be 0. Okay. Finally, so that the steady state error is 0. So you just design the PI. Okay. So this one is you repeat again, Jack, just now. Okay. Okay. Any questions? Any questions?
Sorry, doctor.
Yep.
After we designed the PI controller, the type of the system is still 0. Am I right?
No, the type of the system now, if you combine, okay, okay, S plus 1, S plus 3, S plus 10. Then you add this one, S plus 0.1, then S. So it's type 1 already.
But now if I calculate the error, should I multiply by S? To find KV, to find KV.
To find KP, KP, find KP. Find KP using this one.
Okay.
Sorry, doctor, could you please go back to where we had calculated the K, please?
This one? This one? This one?
The second last question. Yeah, this one, please.
Okay. Then this is the finite value is not equal to 0. That's why use PI.
But doctor, the equation, the transfer function that we used, is it the closed loop one?
This one, closed loop. Which one? Which one, brother?
For the K. To find the KP, please.
This one. This one.
Yes.
So?
Is it the open loop transfer function or the closed loop?
Yeah, GS is a K, GS, open loop. GS is open loop. K is using the one that we calculate, then you insert inside, multiply with the open loop transfer function, which is this one.
Okay, doctor. Thank you.
All right.
Excuse me, doctor.
Yeah.
What would be the circumstance for us to use KV for the error?
No, the original system is type 0. So we must maintain using KP. If the system original is type 1, so you use KV.
Oh, so
So
it
in this
depends on the
case,
original.
The original one.
The original, okay.
Yeah. So if you look here, if we calculate the last part, we calculate the last part, KP of the last part, KP is equal to limit s to 0, okay, AT s plus 0.1. This is the PI, and s plus 1, s plus 3, s plus 10. Okay, so when you simplify, so you will get what? Infinity, am I right? Because of this n. Okay, that's why ESS 1 over 1 plus KP 1 over infinity, and it becomes 0. N.
Yes, understood.
We,
Thank you.
okay. We cannot use KV. We cannot use KV, no, because the original system is type 0. So we maintain the KP. So the last question is question number 2. Yeah. Chung Hoi Ki, can you read for me?
In another application, the system in figure Q1.1 with the root locus in figure 1.2 is being used again. This time, the system is required to have faster settling time Ts equals to 2s with the damping ratio zeta equals to 0.5. And determine the new location of the dominant closed loop poles required. Design a PD controller to satisfy the settling time requirement. Sketch the root locus of the system with the PD controller included.
All right, share. Okay, so question number 2, the new one is 2 seconds, zeta 0.5. The old one is 2.6 seconds. So if you look here, we want much faster, 0.6 seconds, okay? So find the new, we have to find the new closed loop dominant poles. Okay, so in this case, TS, yeah, okay, which is equal to 2 seconds. Yeah, 4 divided by 2, 32. Okay, and then zeta 0.5, which will give you theta 60 degrees. And so theta, this is zeta 0.5. Real part is 2. Imaginary part. Imaginary part. Ika? Macam imaginary part. Ika? mg divided by 2. Okay? mg divided by 2. So mg is equal to, okay, mg and just 60 degrees. So that's why the new closed loop dominant pole -2 plus G 3.46. Okay.
Doctor,
Yep.
if we straight ahead use the angle 60 to
Yeah.
get the dominant pole from the graph, is it
From the
okay as
graph.
well? Yeah, if we just use
Okay,
good,
yeah, he used the previous plot,
Locus.
isn't it? So you print two lah. You print two, one for Q1, the second one for Q2.
Yes, doctor.
Understand? Okay. Also can, no problem.
But the value with like after trying, I can find out that the value is quite different. I get 2.5.
2.5. The one that I get?
3 point.
This one.
You got 3 point for the imaginary part. I mean, you got 3.5. So there's almost a difference of 1. Would it be acceptable or?
Acceptable.
Okay, doctor. Thank you.
Okay, J2. 20, not acceptable. Not acceptable. 20. Okay. Then we continue for GPD. See? Okay. Okay, so continue. So you will get the angle of ZC is 23.14 degrees. Okay, just calculate that using negative criteria. So you will get something like this. So -2. Tangent 23 for this, 3.46 divided by x. X is equal to 8. This one, x. Okay. So that's why your ZC is equal to 2 minus 8. So you get minus 10. Okay. So yes. Okay. But when you combine the open loop and the PD controller together, so it will cancel out. Okay, cancel out. So the gain K now is 12.97 and 2.46. Okay. So what is KP? What is KD? So UPD. K S plus 10. So GPD is equal to 12.97. S plus 10. Okay. So KP 12.97. KD equal to 12.97 multiplied by 10. 129.7. Okay. And finally, the plotting. Zeros here. So it becomes The locus has changed, no curvy, straight to the straight. Okay, because this one has cancelled each other. Okay, guys, I think that's all for the sharing session. So I hope we can try your best, inshallah, for tonight test. I make dua and prayer, inshallah. All my students will pass 15 over 15. SEU over SEU. Okay, inshallah. So I take this, I will share the link for the test tonight, Zoom, start from 9 until 10:30 p.m. So I meet you tonight, okay? You must go to the e-learning, according to your section 5 and 6. So you read the instruction first. So I will give you the password about 10 minutes to 9, okay? 10 minutes to 9. Please on your camera, use 2 devices. Use camera, front camera and side view, okay? Using mirror or whatever you have, okay? Any questions, guys? Any question? Yes, Alan.
About graph tu macam mana betul?
Graph.
We have to print. We have to print it. Macam mana? Kita kena print.
The best way is you print lah. If you don't have printer, you share with your friends yang ada printer. Because it's very difficult if you want to use a protector on your screen. Okay, make effort lah, to print out. Or if you don't want to print out, you take the zeta value, find the theta, and then find the imaginary part, and then find the real part. But you have to calculate, to find the dominant pole. Any question?
Excuse me, Doctor.
Yes, Muhammad.
Can I use screenshot and use a protractor?
Screenshot, and then use protractor. Oh, that one. How you do it? I don't know.
I can say screen. I can
okay.
say screen.
You can try, but as long as the value is in the acceptable range lah. If the dominant pole is -2 plus J4, if you do your own method, you will get -20 plus J40. Of course, it's wrong lah. So it must be in the range of acceptable. Omar, can't hear you. Speaker.
1 minute.
Can't hear you. Louder. Yes, Omar. Omar.
Can now hear me, Doctor?
Okay. Now.
The accuracy is no decimal point. So if 60.5 angle, so it is only 60. Can?
Yeah. 2 decimal point. All calculation, 2 decimal point.
Okay.
Okay.
Okay, thank you, Doctor.
Anything, guys? Atika, any question? Liana?
Yes, Prof, no question.
No question, Okay, very good. Understand. So only one set not discussed, I think 2018, 2018-19. Okay. You want a solution, 2018-19? Guys? You got solution ke? 2018-19. I share in the WhatsApp. Okay. Okay. I share the solution.
Right, Prof. Thank you, Prof.
2019. Okay. Thank you very much. Okay. Selamat Hari Raya. Aidilfitri. Next week no class. Bye.
Thank you, Prof.
Terima kasih, bro. Selamat Hari Raya, bro.